So I'm working through work energy problems. Here's another problem that I made. I will say that I'm doing a series of problems, and these are all work energy problems that don't have to use potential energy. I just think it's easier to start off with that case. So let's talk about, I'm going to get into this problem in a second. Let's talk about the work energy principle in general. It says the work done on an object is the change in energy. And if I pick my system correct, then I do need to always pick my system. So I'll just put system, because that tells me what forces do work, and it also tells me what kind of changes in energy I have. So we're going to pick a system. Then I can say work is F dot delta R equals F delta R cosine theta. So this is the force, and that's the displacement of how far that object moved with that force, and this is the dot product. And one way to do the dot product is to take the magnitude of the force, the magnitude of the displacement, and the cosine of the angle between them. And then in most cases, we're going to have the change in energy is going to be a change in kinetic energy, where kinetic energy is 1/2 mv squared. Okay, let's get to the problem. This says a 5,000 kilogram crash test car. I wrote this question. That's kind of weird. Crash test car test. Well, you know what I'm talking about. It's a car. They're testing the crashiness. And it's moving towards a wall with a speed of 60 miles per hour. And I converted that for you. So let's say V1 equals 26.7 meters per second. M equals 5,000 kilograms. When the car hits the wall, the crumple zone compresses 0.6 meters. So let's call that delta R is 0.6 meters. I'm going to draw a picture in just a second. What's the average force the wall exerts? Okay, so let's look at a picture. Here is my car. Maybe not the best car. Moving that way. And then it's going to crash into a wall. And there's no one in it. It's a test car. And it looks like this. I'm having trouble drawing a crashed car. Okay, that's good. And so the distance that this crashed, so here it was before, and there it was afterwards. So this distance, delta R, is 0.6 meters. That's the crumple zone. That's how much distance it moved. And so if we think about it as the system of just a car, then we have a backwards pushing force from the wall. We have a downwards gravitational force, mg, and then we have an upwards normal force from the floor. So I need to find the work from all of these. So work is by the normal force is going to be the normal force dot delta R, which is going to be N delta R cosine theta. But if this is moving that way, and the normal force is that way, then the angle between them is 0. No, I'm sorry, it's 90. And the cosine of 90 is 0. So this is going to be no work. The work done by gravity is going to be mg delta R cosine theta. And this is the theta between gravity and the displacement. Again, that's 90 degrees, so it's 0. So that means the only work I have is this one. So F, the work done by the wall is going to be F wall delta R cosine theta. So what's the angle between this displacement and that force? And the answer is 180 degrees. And the cosine of 180 is -1. So this is going to be negative F wall. And that's the magnitude of the F wall, delta R. And what does that do? Work done by the wall is going to be equal to negative F wall delta R equals delta K equals K2 minus K1. Now, if it crashes, the final kinetic energy is 0. It stops. So now I can put in my value for K1. I get negative FW delta R equals negative 1/2 mv1 squared. Now I just want to solve for F wall. So the negatives cancel. F wall equals mv1 squared over 2 delta R. And let's just put in my values. I get 5,000, 26.7 squared over 2 times 0.6. So here's my calculator. I'm going to say 5,000 times 26.7 squared divided by parentheses, because I got two things down there, 2 times 0.6, which I could just do in my head. Enter. And I get, a huge force. 2, let's write that in scientific notation. FW equals 2.97 times 10 to the 3, 10 to the 6th. Did I count that right? 1, 2, 3, 4, 5, yep, 6. 6 newtons. So, a huge force. And you can see that the problem is this speed. If I double the speed, my force is going to increase by 4 times because I'm squaring that speed. Okay. How do you know to use work energy in the system other than me saying, hey, use work energy? We use work energy when we don't care about direction and we don't care about time. In this case, I don't care about how long it takes. I just care about the position, the change in position. I knew that it moved, right? I know the change in position. I don't care about the direction of the velocity. I don't care about the direction of the force. I just care about the magnitudes. Work energy is what you want in this case because work energy is a scalar equation and it doesn't depend on time. Okay, I'm going to do another problem. It'll be in another video, so you'll have to see that one. I'll see you there.